Hello students, today we are going to solve one problematic question on single step matching using Smith chart. So for that I am going to consider one problematic question. Single step matching using Smith chart. So I hope you are all familiar with the basics of Smith chart and what a single step matching is. So the question is, determine the location as well as length of the single step match. Okay, this is the question, and they are given that load impedance ZL is 50 minus J 100 ohms and characteristics impedance Z0 is equal to 75 ohms. Okay, so we are going to solve this problem using Smith chart. So we can do this step by step. Step 1. Since the load impedance and the characteristics impedance values are given, so the first step 1 is, first we should find what is normalized impedances. So normalized impedance ZL dash is equal to ZL by Z0. So we know that ZL is, it is 50 minus J 100 ohms and Z0 is 75 ohms. If we divide this value, so we will get it as 0.667 and minus J, if we divide this one, it is 1.33 ohms. So this is normalized load impedance ZL dash. Step 2. Since we got this normalized load impedance, so now we can just locate this normalized load impedance. So I am just considering that point as, locate the point A. I am considering that point as A. Okay. So we can just locate that point by considering R is equal to 0.667. That is in R circle, we can just trace this 0.667. And in reactance circle, it is 1.33. So since it is minus J 1.33, so in Smith chart we know that reactance is below the horizontal axis. Okay. So just assume this is your Smith chart. You can just take your Smith chart. So in this you can just do parallelly. So this is center of the Smith chart. So in the Smith chart we know that left hand side is open circuited end and the right hand side is nothing but short circuited end. Okay. Now step 2 is R is equal to 0.667 and X is equal to 1.33. Since it is minus J 1.33, obviously which will be in the below the horizontal axis. So you can just locate this in R circle and by considering that X circle. So I think approximately we'll be getting at this point. Now we can just name this point as A, which is nothing but normalized load impedance ZL dash. So this will be a second step. So the center of the Smith chart we can just name it as O. Now step 3. In step 3 we can just draw a straight line from the origin or center of the Smith chart up to point A. This is step 3. Step 4. So in step 4, by considering this OA as radius, we can just draw a circle. So this is called as impedance circle, or we can call it as an S circle by considering OA as radius. Step 5. So in step 5, we can just find what is normalized load admittances. So in step 5, extend this line OA in opposite direction, that is diagonally in opposite direction, like this. So by extending this line OA diagonally opposite direction, so we'll be getting 2 points. One is intersection of S circle with this straight line. So now that is called as YL dash, that is normalized load admittance. Now I can say that point as B. Okay, and we'll be getting the one more intersection point, that is this straight line, and which cuts the outer rim of this Smith chart at this point. Okay. Now we can just find what is lambda at this point. Now this lambda is, it is 0.09 lambda. If you can just see your Smith chart in clockwise direction, it is 0.09 lambda. So this is step 5. Next one is step 6. So step 6, we can just highlight the unit conductance circle. that is already there is a circle like this in your Smith chart. You can just highlight like this. This is unit conductance circle. So by tracing this unit conductance circle, highlight this unit conductance circle, so we'll be getting two intersection point. One is here and one is at this point. Now we can just name this point as C and this as D. Okay. So here either C or D will be the stub position. So we can just select either of this point by considering, that is by traveling in clockwise direction, the point which is nearer to the load admittance. So in clockwise direction, the point which is nearer to the load admittance is point C. Okay. So in step 7, we can just draw a straight line from the origin or center of the Smith chart through point C and extend that line up to the outer rim of the Smith chart. So we'll be getting an intersection point of this straight line with this outer rim of the Smith chart. Now similarly, you can find what is lambda at this point. So lambda at this point is, it is 0.18 lambda. Okay. Now what can we do in step 8? Since we know the distance between load admittance and this is the stub. The stub that can be connected at this point. What is the first question is, we can find what is the position of the stub. That is nothing but the distance between this. Okay. Now what is this distance? It is equal to 0.18 lambda minus 0.09 lambda. What's the difference now? It is 0.09 lambda. So S1, that is the location of this stub, is 0.09 lambda. So what's the next parameter? So next parameter is, we should find what is the length of this stub. And before doing that length of this stub, and we can just find what is the x value, that is acceptance value of the stub. This is the stub. So this is the point where we connected this stub. So you can find what is x at this value. That is only that reactance. What is that? It is J 1.6. So this is plus J 1.6. Why? Because it is above the horizontal axis. So we can just find that length of the stub in such a way that, that is the length of the stub that can be adjusted in such a way that the susceptance of the stub that can be cancelled with the transmission line. Okay, so we know the susceptance of the stub, that is plus J 1.6. To cancel out this plus J 1.6, what should be the susceptance of the transmission line? It should be minus J 1.6. Only then both the values get cancelled. Okay, so you can just locate that point with minus J 1.6. If you just look into the Smith chart, so approximately here we'll be getting that point, that is minus J 1.6. Now what is this point? Now say this point as E. Okay, now this is the point where the susceptance of the stub is cancelled with the susceptance of the transmission line. Okay, so in this next step, what can you do is, we can just draw a straight line from the center of the Smith chart through this point E. Extend that line up to the outer rim of the Smith chart. Name that point as E now. Now at this point, see what is lambda at that point is. So lambda at this point is, it is 0.338 lambda. Is it clear? Okay. Now what are we going to do? We are going to find what is the length of the stub. So always the length of the stub that can be determined by taking the distance between the short circuit end to this point. That is, say for example, this is your load and this is your stub. Okay. So now this is your short circuit end. So what is length of the stub is nothing but what? So from here to here, that is, this is the position of the stub, that is stub. Okay, the point where the susceptance value is cancelled, and this is nothing but short circuit end. So this distance you can just find. So where is the short circuit end from your Smith chart? So always length is in between these two. So this distance. So already at short circuit end, we know what is lambda is. It is 0.25 lambda. Now we can find what is the differences. So this is nothing but length. So the length of the stub L is equal to, what is the lambda at this point? It is 0.338 lambda minus 0.25 lambda. Now what's the differences? 0.088 lambda. So now this is the length of the stub. Suppose if the question is, we should find what is normalized load admittance, and in that case you can find what is that YL dashes. So in your Smith chart, if you just see that YL dash, that is nothing but it is 0.3 plus J 0.6. This is normalized load admittance. So if it is a single step matching problem, which means that we can find what is location of the step and length of the step. Okay. So I hope you are clear with the step matching problem using Smith chart. Thank you one and all.